we introduce a method for the fast computation of complex multi-contact animations in cluttered environments for arbitrary length characters. The method computes a trajectory for the center of mass of the character, which is constrained kinematically and dynamically by the contacts active at each specific phase. Once a COM trajectory is found, a sampling-based second-order inverse kinematic solver is used to generate a whole-body collision-free motion along it. A second video is dedicated to present the method, while the present one focuses on the results we obtained. The first series of results demonstrates a direct application of our method. Here, in this simulation of a twister game, the next contact is randomly chosen for a given limb among a set of discretized candidates. The characters move each at a time in close interaction. At the end of this demonstration, the characters remove contacts instead of adding them. On the quadruped, it appears clearly that the center of mass aligns with the two remaining effectors before the last contact is removed. Even though our method is best suited for non-highly dynamic motions, one strong advantage is that it will always find a solution. Here, when the humanoid stands on its hands, no static solution exists. However, our method is able to compute this motion. This scenario further demonstrates the versatility of our method, with a virtual insect adding and removing contacts while climbing up this wall. In this second series of results, we integrate our method with an open-source contact planner. The only specified inputs are the start and goal configurations of the character. The contacts are selected and the whole motion generated in a few seconds, as shown in this first climbing example. Another example is demonstrated with this humanoid crossing a set of uneven stairs. This last series of examples shows how we can obtain variations on the same scenario. Here, the character sits on a chair, stands from it, and sits again, but this time avoiding a column. Interestingly, this time the right arm is not used for contact creation to avoid collision. With our method, obtaining variability in the motion is achievable intuitively. In this example, the transition points are translated along the z-axis to generate 3 variations of the same motion. Because the method is fast, it could be used for artistic authoring to simply generate new motions on the fly. Another option to introduce variability is to design simple cost functions that will influence the shape of the COM trajectory. In this example, we generate various motions for the HRP2 robot along the same contact sequence. If we formulate a cost function that minimizes the distance traveled by the COM, we can obtain this motion where the robot looks tired. On the contrary, by maximizing the lateral amplitude of the COM, we can obtain a groovy motion. Here, we constrain the trajectory to be as close to the ground as possible. In the spirit of the famous silly walks from the Monty Python, we can even generate weird behaviors, such as in this case, where the COM is constrained to be as much on the right side of the rabbit as possible. The advantage of specifying such cost functions is that it does not require the artist to manually define the control points for each element of terrain the character will encounter. In the next few examples, similar cost functions are used to navigate a set of rubble.